Unit 4. I introduce these three terms. I introduced those three terms to you. And here's where we talked about them. If I turn a figure, does it change its size or shape? No. So what did we know about the two triangles? They were congruent. Okay. If I slide a figure, let me go back to my original. If I slide a figure up, down, left, right, will it change the size or shape? So what do we know about the two triangles? Congruent. And I can't physically reflect one on here, but if I reflected it, will it change the size or shape? Nope. So we say they are congruent. Does anybody know the term, the vocabulary term we referred all three as? These are all transformations, yes, all transformations. But because they made the result congruent to the original, we called them rigid motions, yes. Okay? Anything that makes an original congruent to the image, we called it rigid motion. Which transformation did we not put up there when we did these? Dilation. Why not? They're not congruent. So dilation's not a rigid motion. But they may not make the triangles congruent, but today when I blow up a triangle or reduce it in size, it'll make the triangles not congruent, but similar. So that's today's topic, is a dilation. Why does it make the triangles similar? All right. So let's talk quick definition first of dilation and why it fits into the similarity unit. Some of you may know already. I'm not sure. Get my act together here. There we go. Enlarges. Is it always an enlargement? Could be a. So enlarges or reduces a figure, and here's where the similarity unit comes into play. Proportionally. So if one side's being doubled, guess what the other sides are being? Doubled as well. All right, it's just not doubled, tripled, quadrupled. All right, if all sides are getting doubled, if one side's getting doubled, they're all getting doubled proportionally. Center of dilation, that's the fixed point where dilations occur. What unit are we in? 7? Unit 9, we do a whole transformation unit where we start talking more in depth about center of dilation and doing dilations. But today it's why when I do a dilation are these triangles similar? That's what I want to talk about. Scale factor. We have heard this term, this unit. Anybody? Just anything. Scale factor. What's a scale? How do I find it? What is it? Anything. It is a ratio of what? Close. Let's get a little more specific. It is a ratio of? Well, just not sides, but what about the sides? There are distances, there are corresponding sides, correct? So this is the ratio of two corresponding side lengths. All right, two corresponding side lengths. All right. Remember we said we had an enlargement or a reduction. If you have an enlargement, here you go, everybody. Your scale factor. If a figure is getting bigger, the scale factor will always be greater than 1. Always be greater than 1. If the figure is getting smaller, I'm going to assume a lot of you are now thinking in your head scale factor less than 1. Not exactly. Okay, not exactly. The scale factor will be between 0 and 1. So I know a lot of questions may come up now. Anything you want to ask about that? Because usually 2 questions come up. Is there possible to have a negative scale factor? The answer is yes. Just pencils down for me. Pens, pencils down. Because I don't want you to write any of this down, but I do want to show you because I think it's good to see. And we're going to deal with it in a couple units anyway. So let's say I have a triangle. Oh, no. Let's say I have a triangle right there in the first quadrant that looks like that. Cameron, give me a negative number. -3. So let's say my scale factor is -3. Here's how the negatives work. 3. Am I going to enlarge or reduce this triangle? Enlarge. It's bigger than 1. So it's going to get bigger. What's the effect the negative has on it? It's going to go through the origin and end up in quadrant 3. That's the effect the negative has. It goes through the origin. So here is what the resulting triangle would look like. It's going to get bigger because it's the 3, and the negative makes it go through the origin. So yes, it is possible to have a negative scale factor. The other question I usually get is, well, what if the scale factor is equal to 1? Scale factor equal to 1? It's the same triangle, right? If it's 1 to 1, the sides don't change length. Good. All right, so bigger than 1, it's got to be an enlargement. Between 0 and 1, it's got to be a reduction. Look at my figures here. Take a look at 1. We're going from A to B, everybody. A to B when you look at it. Are we getting bigger or smaller? Let's answer that easy question first. Bigger or smaller? Bigger, obviously. So this is an enlargement. And can we all agree on that? Enlargement? Now it's asking, hey, you find the scale factor now. What did I blow this up by? Well, remember what the scale factor is. The ratio of 2 corresponding side lengths. Can you guys count 2 corresponding side lengths on that polygon? Okay, go ahead. Go ahead. Count 2 corresponding side lengths. There's a couple different places you could go. I'm assuming people are going to use the bases here. So 2 corresponding side lengths. Let's see. I'm counting 1, 2, 3, 4 on figure A, and I'm counting 1, 2, 3, 4, 5 on figure B. Everyone else agreeing with me? Those are 2 corresponding sides, 4 and 5. You told me this was a what? Enlargement or what? Reduction? So what do you know? Look up top. What do you have to know about your scale factor if it's an enlargement? It's got to be bigger than 1. So you can't tell me right now that your scale factor is 4 to 5. Why not? That's not bigger than 1. If it's an enlargement, it's got to be bigger than 1. So it can't be 4 to 5. It's got to be 5 to 4. So my scale factor, 5 to 4. That tells me, hey, it's getting bigger. We see that, why it's got to be 5 to 4 versus 4 to 5. All right, let's go. 1 doesn't make you great. A to B, enlargement, reduction. That's a reduction. That triangle's getting smaller. All right, there's a couple places you could go ahead and count corresponding sides. Go ahead. Give me 2 corresponding side lengths if you haven't already. What did many of you do? Did you do the bases or did you do the horizontal sides or the vertical sides? A lot of people did vertical. Okay, so 1, 2, 3, 4, 5, 6, and 1, 2. This was a reduction, right? What do you got to know about your scale factor? Between 0 and 1. Nothing can't be bigger than 1. So am I going to go 2 to 6 or 6 to 2 here? 2 to 6, 1 to 3, whatever you prefer. Okay, but it's got to be 1 to 3, 2 to 6. Cannot be 6 over 2. That would be bigger than 1. So my scale factor, I'll do the reduced version. That's how I roll. 1 to 3. Everyone okay? We all good? What type of scale factor I look for, depending on if it's an enlargement or reduction. All right, we got one final thing, and then for what, 3rd day in a row, you guys get to start your homework early? Go ahead and graph A, B, C, D, E, F. A, B, C, D, E, F. Go ahead and graph it up.
Could there ever be like a ratio where both would work?
They wouldn't be similar then. What do you mean, on one pair of sides and a different ratio on another pair?
No, like 2 numbers. Like, you know how we had 4 and 6? They'd be like different numbers, but.
And not the only way I could see that, Cameron, is if they could be reduced. You're not going to have 4 and 6 and 5 and 10. That shouldn't have, because then that would mean that they're not similar. Okay? If they're similar, they're all in the same ratio. Okay, so we have them graphed. They're telling you that it's a dilation. Now prove to me that the triangles are similar. The triangles are only going to be similar if what's going to happen here. Talk with me. I don't want to give this away. The triangles will be similar if what? What are in the same ratio, Will? They're all 3 pairs of sides are in the same ratio. How am I going to know if B, C, and EF are in the same ratio? Distance formula, yes. And I'm going to make it easy on you. All right. I know it's painful doing 6 distance formulas, so we'll break it up. Ready? You guys, what corresponding pair do you want? Group 1. AB and ED. Okay, you got it. So your group 1's got AB and ED, simplest radical form like usual. Group 2, you got a preference for what's left over? BC and EF, you got it. And then group 3, sorry, it's not that like it's a big deal, but you guys now have AC and DF. Simplest radical form. Here we go. Before, make sure we jot it down. Group 1, what do you got for me for AB? 2 radical 2? I have breaking down the square root of 8. Square root of 8, remember, breaks down into 4 and 2, right? Square root of 4, 2, and then bring down the radical 2. Good? No, it's 2 radical 2. I wasn't disagreeing. Sorry about my tone. I apologize. ED, 4 radical 2, yes. Group 2, BC. Radical 10, yep. And then how about EF? 2 square root of 10, which is breaking down 40, yes. And group 3, how about your AC? Square root of 10, oh, looked like there was isosceles, huh? DF? 2 radical 10, yep. So I'll give everyone a minute to jot down those, and then we'll talk, are these actually all in the same ratio or not? Because I can tell that, this, obviously, these 2 pair are, but is that the same ratio as AB and ED? Okay, so let's talk. We had 2 radical 2 corresponding to 4 radical 2. We had radical 10 corresponding to 2 radical 10. And we also had another radical 10 corresponding to 2 radical 10. Can I have somebody's algebraic skills show me? Because yes, those 2 are in the same ratio. They're the exact same radicals. But are these 2 the same as that one right there? Can I have some help algebraically breaking these down even further? What's going to cross off here? What could I cancel out? Or just what's this break down to in general? Radical 2's can cross out, and what's 2 over 4? So this breaks down into 1/2, right? Okay, let's keep going. What can I cross off here? The radical 10's, but you're just not left with 2. Be careful. What's still in the numerator? A 1. Yep, so this is also 1/2. 1/2. All 3 pairs of sides are in the same ratio. What do you know about the triangles? Triangle ABC, similar to triangle DEF. Going to give me a reason? And I don't want to, all 3 pairs of sides are in the same ratio. We have a name for it. Emma, what's the name for it? They all have the same scale factor. 3 methods of proving triangles congruent. Ooh, almost said it. Similar. Which one did we just show? Okay, I'm not going to go on any further. There we go. You got 2 algebra problems to the nearest hundredth, and you have the dilation problems in your homework.